Another episode. Today we're going to be talking about the surface point tangent space characterization theorem. Let's get straight to it. So what's the claim? Well, if S as a subset of the n-dimensional real space is a K surface and X is some point contained therein, then the tangent space at X of the surface S is a K-dimensional linear subspace of the n-dimensional real space. If, moreover, phi, which maps this subset U of the K-dimensional real space, maps it into, or rather onto the surface S, and if it is a K-chart, and such that X is equal to phi at U for some point U in U, then the tangent space at X of the surface S is actually equal to the span of the following vectors, the partial derivatives of phi with respect to the individual variables at the point U, to UK U. All right, how do we prove this? The proof is simple. We observe that it is sufficient to prove this equality. If we do, then we prove the first claim, that is that tan S is a K-dimensional linear subspace of N. This follows from this equality. So if we prove it, we also get this claim for free. So how do we prove the equality? Well, we want to show the equality of two sets. So we will show that if an element is a member of one set, it is automatically the member of the other. So we will prove two implications and we'll get an equivalence, right? So proof, part 1. Assume that V is a non-zero vector such that it is an element of the span of these partial derivatives. Right? This means, by definition, that V can be expressed as some linear combination of these partial derivatives. So we write this the sum for some coefficients alpha of the partial derivatives at U. And we also observe that all of the alphas cannot be zero, right? At least one of them is non-zero. So we say that alpha I is not, well, rather alpha 1, alpha 2, etc. up to alpha k is not the zero vector. All right. Well, put some CT, we'll show it as a curve, equal to phi of U1 plus alpha 1 t of U2 plus alpha 2t, U3 plus alpha 3t, etc., all the way to UK plus alpha kt for some variable t from the open interval ranging from negative delta to positive delta for some delta positive, and choose the delta so that the argument of phi were contained in U. Right, now, why did I say that clearly C is a curve? Well, apart from the naming C, we can see that C is a product of function of a single variable, right? That would be this vector inside the as the argument of phi. So this is some well, no doubt this inside this argument is a curve, right? It is a boring curve, but it is a curve. And if I take phi of this curve, it will still be a curve because phi is a continuous map, right? So we continuously map some curve someplace else into some other space. It will still be a curve. So this is a curve, and moreover, and that's important, the curve is non-singular because the original curve inside is non-singular because, well, if we try to take the derivative of it, we will get a non-zero vector from here. Right, we would get the vector alpha 1 to alpha k, which are not the zero vector, as we've established. So it is non-singular, because if we then apply the phi map, nothing can go wrong. It is a beautiful homeomorphism, right? And then we also know that by design, and I should also mention that when I write u1 through uk, this is equal to this is written out the point u, right? So clearly phi 0 or phi of 0 is equal to phi of u, right? Now we know from our assumptions that this is also equal to x. Okay, now moving on, if we take the derivative of c at 0, we obtain by chain rule this identity that will be the sum ranging through 1 to k of alpha 1 to alpha k of the individual partial derivatives at the point u by the chain rule. But this, we know, is equal to v from up here, which means then that c prime at 0 is in fact inside the, well, it is equal to v, which is part of the tangent space, which is precisely what we wanted to prove. So this concludes part 1. Now, moving on to part 2, we will show the converse membership, right? So we will assume that V is an element of the tangent space at x of the surface S, and that it is non-zero because that's a trivial case which we won't bother ourselves with. And we will show that it is in the span of the partial derivatives of phi at u, right? So how are we going to do it? Well, that's not that difficult because we know that by definition there must exist. So by definition there exists a non-singular parameterized curve C, which maps some interval I as a subset of the real number line onto the surface S. We also have some point t0 in I, such that C at t0 is equal to x, right? And this is the important bit, C prime, or the derivative of C at t0, is equal to V. So we have this by the definition of the tangent space and what it means for V to be an element of the tangent space. Right, without any loss of generality now, so log, without any loss of generality, C of I is a member, well, is a subset of phi of u. In other words, essentially, this the interval on which the curve is defined is not too large, right? The curve is contained on this map, right? Because the surface may be a composite, surface, meaning it may be non-simple, meaning that it can be only written, its atlas may at minimum contain 2 or more maps, right? Which we want to exclude because we would like to use the theorem, which we have covered last time. That was the, what was it? The curve on a surface theorem. And one of the requirements of the curve on a surface theorem was that we were dealing with simple surfaces, right? So we will restrict ourselves to just the image of a single chart. And as such, this will essentially simulate it being a simple map, a simple surface, because for all purpose it will be. Our setting will be simple. It doesn't matter that outside there is some bigger world with other charts, right? So it can be without any loss of generality, because if it were too large, then we could simply restrict it. And the important bit is that that our T0 is where we need it to be, right? So that's without loss of generality. And then by the previous definition, so the previous theorem, then by the surface, or what did we call it? The curve on a surface theorem. So curve on a surface theorem. C can be written as the composition of phi and u. For the u from the theorem that we had, that being for u being equal to phi inverse composed with C, which maps the interval I into u. Okay, but then, so hence, C prime, or the derivative of C at T0, is equal to... Also, I would like to mention that we have... we don't have a very good notation, because we notate this is a function and this is a point, right? So I apologize for that. But with some ingenuity, we can decide that this is actually equal by the chain rule to the following sum, so that we have I iterating through 1 to k. Then we have the individual partial derivatives with respect to ui at the point ui, right, times the derivative of u at t0, right? Oh, I'm missing because in the derivative that we are doing, u is a function, and we are taking the derivative at t0. So by the chain rule, this is what we obtain, and we observe that since u is a map which maps, it is a map of a single variable, right? And since it is a function of a single variable, this notation makes sense. We don't have to use dels. Now we observe that this is in fact an element of the span we were talking about earlier, right? I'll explain why in just a moment, right? So let's point you all the way. We have 1 all the way to uk at u. Why? Because t0 is a fixed constant. So no matter what this function is, no matter how crazy, the output is a single number, right? So we could substitute it with some alpha I. And here we have some linear combination of these vectors, right? So this in fact is a and each one of them is simply modified or scaled by this number. So overall, this is some linear combination of vectors from this subspace, and thus the product, the output, will be an element of the span of these vectors of this subspace, and thus we have shown that whenever we have a vector which is a member of one or the other set, it is automatically a member of the opposite set. And thus we have shown set equality, which is precisely what we wanted, and this concludes the proof.